In this video, we'll see about electric field strength at a point on the axis of charged ring. See here in the diagram, you can see on this ring, there is a charge Q uniformly distributed throughout the ring. Center of ring is O, and let us take the radius of the ring as R. Let us calculate the electric field intensity at point P. The point P is at a distance, say some x from the center of the ring. So the charge is uniformly distributed, as I said. The charge is, we have to find out the electric field intensity at point P. Okay. So to calculate the electric field intensity at point P, let us assume, this ring is, we can divide into infinitesimal parts or segments. Okay. And this segment has charge, say dq. So due to this, what is the electric field intensity at point P? We'll see first. And after that, the small segment dq, the distance is, this is capital, the radius of the ring is r, and the point P is at a distance x from the center of the ring. So this, from the small segment of the ring dq, the distance of point P is, from diagram you can write r square plus x square. So let us see the direction of electric field. See, due to this ring, say here, let me take as some m, from m to p. So the electric field intensity direction will be line joining from m to p, that we can take. Okay. So the electric field due to that small segment dq will be directed in this direction. This we can write as dE bar. This we can take as theta. So what is electric field intensity here due to that ring, due to that small segment of the ring? dE bar is equal to the value you can write k into the charge on the segment we have taken as dq by distance square. What is the distance? R square plus x square, root square of it, r square plus x square. Some unit vector if you take as r cap, into r cap you can write. So if you consider only magnitude, let us take only magnitude, then dE is equal to k into dq by r square plus x square. So this is the electric field intensity at P due to small segment dq. The electric field is directed in the given direction dE bar, it makes an angle theta. Okay. If you resolve that into components, and this becomes dE cos theta. And another vertical component, the normal component is this, and this one is dE sin theta. Okay. So here let us take another segment. Exactly opposite to the first segment we'll take. And due to this also, electric field intensity at point P is directed in this direction. Due to small segment n at point P, the electric field intensity is this. Again, you resolve this into components. This is also theta. If you resolve into component, along this, it is dE cos theta, and the vertical component is dE sin theta. So what is happening? The vertical components dE sin theta, due to opposite segments, exactly opposite segments that are taken on the ring, cancel each other. The electric field components due to opposite segments of the rings produced at point P, the electric field produced at point P, those vertical components of that electric field are getting cancelled each other. See, this d sin theta and d sin theta same in magnitude and acting in opposite direction. So what is the remaining? The remaining is along x-axis or along the axis of the ring. So axis of the ring only, all the electric fields are aligned. Therefore, what we can write is, therefore total electric field, if you take it as some dE t, is equal to dE cos theta. Total electric field, if you calculate total electric field at point P, we can integrate this total horizontal component. So dE cos theta. So if you substitute And here what is cos theta also will write in the diagram. See, the cos theta is what? X by root over r square plus x square. Let us substitute this dE here. K means K is 1 by 4 pi epsilon naught, that you remember. So K dq by r square plus x square, cos theta is x upon r square plus x square. Take the integration. So here kx and everything is constant. We can write out of the integral kx by r square plus x square power 3 by 2 integral dq. So if you integrate it, finally total integral dq is the total charge on the ring. Okay, so kx by r square plus x square power 3 by 2 into total charge given is q. So this is the total electric field on the axis of the ring. If you write in the vector notations, along it is the electric field is directed along the x-axis, you can take I cap. Magnitude kx by r square plus x square into 3 by 2. So this is the total electric field equation. Now we'll see a few different very important cases in this. Let us now we'll find out at what point on the axis of ring the electric field will be maximum and how it is varying, that also we'll see. So first case, at a ring, a center of the ring, what is the electric field, we'll see. In the case 1, first case, if you take at center of ring, that is x is equal to 0. Therefore electric field intensity is 0. So where it will be maximum, that also we'll see. So maximum in the sense the differentiation value, if you differentiate the electric field with respect to x, then if E is maximum, see here in the equation, if you observe the final equation of the electric field at point P, and the electric field is directed away from the positively charged ring along its axis in the direction of I cap, positive x axis. And one more point we got, at the center of the ring the electric field intensity is 0. So at the center of the ring it is 0, but if you observe carefully at longer distances the denominator value keep on increasing. So at any particular value, for example we take infinite, at infinite the electric field intensity will be 0. Generally electric field intensity we take 0 at infinite. That means what, at the center of the ring it is 0 and at infinite also it is 0. There must be some maximum value at any distance from the ring, on the axis of the ring. So let us calculate that. So in this case, if you get that value, what is the case we are considering? E tends to E maximum. When E is equal to E maximum, then dE maximum, differentiation of that maximum value with respect to x, is 0. If you differentiate above equation, just you take it as homework, and we get x value we get as r by root 2. R is the radius of the ring, you know that. So we get x value plus or minus r by root 2. Okay, that means what, at x, that is on the axis of the ring, at a distance r by root 2. Okay, this is radius r at a distance r by root 2, somewhere here, say electric field is maximum. So let us draw that graph here, how it is varying, the radius. For example, somewhere at this point, the distance of the point is r by root 2, the value of electric field is maximum. Okay, similarly, if you take the if you draw the graph left side of the ring at the same distance, the value of the electric field intensity due to ring will be maximum. And if you draw the graph at the center, it is 0. So, and it becomes maximum here and gradually decreases, becomes somewhere 0. In the similar manner, the variation, you can see here it is a maximum at this point, the graph, this value is maximum, and finally somewhere here it becomes 0. Okay, so electric field at r by 2 distance is maximum. This is the variation of the electric field along the axis of the ring. Okay, so what is the maximum value? So E maximum will be E maximum at x is equal to r by root 2. And if you substitute this in the equation, the E maximum value that is in place of x you substitute r by root 2, we get the maximum electric field value. This is k into 2q by 3 root 3 r square we get. If you see along a y-axis how electric field is varying along with the distance, we took electric field value of electric field on the y-axis, and we observe how this electric field is varying along the axis